Hello, my name is Tony, and I'm a second-year PhD student at MIT with Professor Luca Carlone. Today, I'm excited to present our newest work on 3D scene understanding. In this work, we present a 3D representation of scenes for actionable spatial perception. In many applications, such as mixed, augmented reality, or autonomous driving, it is important to have a 3D map of the environment that ideally goes beyond the geometry of the scene by semantically labeling the objects. This is important for high-level understanding, such as in safety-critical applications like self-driving cars, where you want to avoid pedestrians or other cars. Ultimately, we want robots to be able to navigate in indoor environments, potentially interacting with humans. Therefore, there is a need to develop simultaneous localization and mapping algorithms, also known as SLAM, that go beyond accurately estimating the location of the robot and the map of the scene, but that also semantically label the scene. Therefore, previous to this work, we tackled the problem of 3D scene understanding by developing and open sourcing a real-time metric semantic SLAM pipeline that we named Kimera, which is able to reconstruct the 3D geometry while semantically annotating the scene by using visual and inertial data, everything while operating in real time. Here I'm showing a top-down view of a large-scale scene reconstructed by Kimera. I will not have time to present Kimera itself, but let me refer you to our paper for details on how Kimera works. In this talk, I will focus instead on how we turn the raw 3D metric semantic mesh into an actionable 3D representation. In particular, we want our new representation to solve a set of problems, or at least to make them easier to solve. First, we want our representation to allow for path planning queries that are semantically meaningful, such as commanding a robot to go to the kitchen. Such command not only requires to know where the kitchen is, but also, if the scene is very large, it requires an abstraction, such as a topological map, to be able to plan efficiently a collision-free path to that room. Moreover, since as humans we prefer to reason in terms of higher-level abstractions, our map needs to encode higher-level concepts such as rooms and buildings instead of just objects. Finally, we would also like to encode dynamic agents in the scene, such as humans. To achieve these requirements, we propose a 3D dynamic scene graph, or DSG. A DSG is a tree-like representation that abstracts a dense 3D model, such as a metric semantic mesh, into higher-level spatial concepts. For example, objects and agents in layer 2, places and structures in layer 3, rooms, as in layer 4, or even buildings in layer 5. This representation is compact, modular, scalable, fast to build, and most importantly, actionable, as we will see next. Our approach is inspired from the work of Armeni and colleagues who presented last year a semi-automatic way to build a similar hierarchical representation, which was focused instead on static scenes. Our representation further allows for actionable queries, such as semantic path planning. It maps as well dynamic agents, and it is built fully automatically. In this work, we use a photorealistic simulator to test our approach. On the top right, you can see a rendered image of the scene. And we also simulated humans in an office space, thereby allowing for dynamic entities, which creates several challenges that we explain later. And we also have objects in the scene that we try to detect, reconstruct, and encode in our DSG. So let's start by describing layer by layer what a DSG encodes. As the first layer of our DSG, we have our 3D metric semantic mesh reconstructed by Kimera. In layer 2, we model objects by their 3D centroid, a bounding box, its semantic label, and its instance ID. To extract objects from the semantically labeled 3D mesh, we first extract all 3D meshes that have a given semantic label, such as a chair. Then, using Euclidean clustering over the 3D meshes, we segment the objects into multiple instances. Once we have the instances, we can compute its centroid and its bounding box. We distinguish between two types of objects: known, for which we have a 3D CAD model in our database, and unknown, which has no prior 3D model. For the known objects, we fit its model by first extracting 3D key points between the estimated 3D mesh and the CAD model 3D mesh. We then match all 3D key points between the source and target models. Of course, this will introduce a significant amount of outlier correspondences, but by using outlier robust 3D registration techniques that we recently developed, we can faithfully register the 3D models. Still in layer 2, we also model dynamic agents, such as humans, robots, and so on. For each agent in the scene, we build a 3D pose graph, a 3D mesh model describing their potentially non-rigid shape over time, and a semantic label. Having dynamic objects in the scene complicates significantly the state estimation of the robot and the mapping. Therefore, we make use of the semantic and inertial information to counter its effects, as we will see later. Let's first see how the human agents are detected and then tracked. We first detect a human by extracting a bounding box in the RGB image using the semantic segmentation. Then we use a graph neural network from Professor Danielides' group that infers an approximate 3D mesh model. And while this approach works fairly well given an approximately clean 2D bounding box of the human, it sometimes returns wrong estimates that we must deal with when tracking humans. For tracking, we build a pose graph with a motion model, such as zero velocity model, for example, where we incrementally add a new vertex upon a new human detection. We further avoid the potential outliers from the detection module and also solve the data association problem by looking at consistency between joints, which accepts new measurements only if the joints displacement between 3D mesh models are reasonable given the time between detections. Here we show the results of the human tracking module, with in blue the pose graph edges and in red the detected human. Clearly, building a 3D mesh with dynamic elements may introduce artifacts that we must address. In our case, dynamic objects both affect the localization and the mapping modules. Therefore, we use an inertial-aided Lucas-Canada tracker, which discards feature tracks that do not follow the expected per-frame rotational optical flow inferred from the gyroscope, and a two-point ransack that also uses the ion rotation to prune outlier correspondences in the feature tracks. On the mapping side, we are able to avoid integrating depth measurements from dynamic elements by discarding those measurements that correspond to pixels from dynamic objects in the 2D semantic image. Then, in layer 3, we encode places and the structure of the 3D scene. First, we define as a place a region of the scene that is not occupied and where the robot can navigate. Two places are connected by an edge if we can go from one place to the other in a straight path. Therefore, the constructed graph is a topological map and allows for path planning queries. We use the work of Olejnikova and colleagues to automatically build the topological graph. We further detect and represent the 3D structure of the scene as a combination of walls, ceiling, and floor, as can be seen in the left figure. Then in layer 4, we construct the room layout of the scene. We encode rooms with a 3D pose, a bounding box, and a semantic label. Connectivity in the graph represents traversability from one room to the other, meaning there is a door connecting both. We do not need to explicitly detect doors, since the topological graph provides us with sufficient information to infer the way rooms can be traversed. All elements in layer 3 have an edge to nodes in layer 4 if they are in the corresponding room. Detecting rooms remains a challenging problem in a general setting. Nevertheless, in our context, we found that a simple technique achieves near-perfect results. In our approach, we make use of the Euclidean sign and distance function, also known as ESDF, which encodes for each 3D point in space the Euclidean distance to the nearest obstacle in the scene. Our insight is that the 2D ESDF is constant almost everywhere in a 2D slice near the ceiling, as can be seen in figure A, where all the values are encoding the distance to the ceiling except when we get close to a wall where the ESDF decreases to 0, meaning it intersects with the wall. Figure B shows that truncating the ESDF gives us a good signal of the room layout. Then, as can be seen in the top right figure, we add a label to each 3D place falling inside an ESDF room, and then use the topology of the layer 3 to propagate the labels to nearby nodes. It then becomes also trivial to connect rooms together and infer the door positions by just looking at which edges connect places in different rooms. Finally, we abstract the 3D scene graph using building nodes. In our case, we have a single building node that encompasses all room nodes. Finally, we have our hierarchical 3D scene graph with meaningful connections between different layers that can be exploited for a myriad of applications, as we detail in our paper. In this talk, I would like to quickly present a semantic path planning query. Here we show a small drone that is requested to reach another room in the scene. The path planning can be done at multiple levels of abstraction, starting from the room layout, then the topological map, and finally the ESDF layer. This approach speeds up path planning queries and allows for semantically meaningful requests. Thank you very much.